Now, in this video, we're going to be talking about strategies for writing proofs. All of our examples are not going to be coming from one particular field within mathematics in order to make this sort of a more general, broad overview. But typically, when students first encounter having to write their own proofs, it can be a difficult transition. Proofs are more than just calculations. Um, you can't just like do the kind of arithmetic operations that we have done, all throughout school and then say that's a proof. That is not a proof, because typically our proofs are going to require justifications. Um, so as we make each step, we're going to have to explain like why we're doing what we're doing and why we're doing it. Imagine that, for instance, there is somebody who is skeptical and you are trying to persuade them that this is in fact justified. So it's going to be more of an argument, and adding those words to a calculation is what usually throws students off because it's different than what we've been doing before. Students often first encounter doing proofs in a course like linear algebra or in discrete math. Sometimes we'll encounter them in other contexts. Occasionally, Calc 2 professors will require that infinite series tests be conducted as if they were formal proofs. Sometimes your math professors will do proofs for you in class, and you are trying to replicate what they are doing, but necessarily what they write on the board also has to be coupled with what they're talking about. And when you do proofs on paper, you don't have that talking component. So you have to write it down and put it on paper and not just assume that your audience will understand it. Now, when you start writing proofs, you also have to think about the audience that you're writing for. Some steps that may seem obvious don't need justification, but as long as they are part of the knowledge base, you are certain is shared with your audience. Appealing to theorems or definitions may need to be employed when that knowledge is not necessarily shared. Again, proofs typically require a brief preamble in order to make it clear what is given, what is being assumed, so that you can lay out all of your premises explicitly. And then at the end, it also should have a closing statement indicating what you were trying to prove and that you have now proved it. Typically, proofs are also done in the most general form possible, unless the statement of the proof to be shown includes certain specifics, and then you will use those specifics, but not any more specific than what is provided. Also, when students need to show that something is true in general, you can't use a specific example to prove an in general case. You have to use unknowns, for instance, real numbers, A, B, C, X1, X2, X3, etc. And in the statement and in your work, it has to be true for any real number. It can't be true just for one particular example. Now, we often in math class will use a particular example in order to make something abstract more concrete in order to help us process it. But that is not a proof, that is a demonstration. And when we're doing proofs, we need to be as general as possible. So the examples that we're going to walk through here are going to be more of a sort of stylistic illustration. Again, because you might encounter this in other classes, not just in linear algebra or discrete math. I have not focused completely on only examples from linear algebra or only examples from discrete math. Instead, some of the examples I've tried to use are maybe examples from, let's say, algebra, things that we know, but then how would we go about stylistically establishing the expressions are in fact the case. Again, we're looking at this from the mathematical perspective, and professional mathematicians deal in proofs. They calculations and arithmetic are certainly important, but in order to make math, it's the logic and the generalizations that are the powerful things, not the instances where they get applied in a specific context, unless you're in applied math. But in any case, we want to talk about proof writing. So in our first example, we want to prove that the solution to a quadratic equation of the form ax squared plus bx plus c is equal to 0, where a, b, and c are real numbers and has the solution of the form x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So we've encountered this quadratic formula in our algebra classes. How would we prove mathematically that this is the case? So there are a couple of different strategies that we can use for this example. So one way, we can derive the formula from first principles. So we can use various strategies in order to reconstruct this equation, or we can just sort of go at it sort of a direct approach. We can replace the form of the solution into the equation and show that it produces a true statement. Now, the hard part about the substitution step is going to be squaring the expression, but we're going to go through both strategies here. Now, if we consider our quadratic equation, this is what we're given, and we want to prove that our solution is of that particular form. We have a, b, and c are real numbers, and we want to find the solution to the equation, and the strategy that we're going to use is to complete the square. Now, to get our equation ready to work with, we're going to divide out the coefficient a through the entire equation so that that first component is x squared. Then we're going to move the constant to the other side of the equation, and we're going to complete the square on the left. Now, the rule for a perfect square is that if I have a form a plus k, x plus k squared, then when I FOIL that out, the perfect square trinomial is x squared plus 2kx plus k squared. So what I want to identify then is that if I want to complete this square, I need to find the value of k by identifying 2k, the coefficient of my x component, to be the value of my x component in the form that I have. So I'm going to say 2k is equal to b over a, and then I am going to divide out the 2 to get my k. Then to complete my square, I'm going to find k squared, which is b squared over 2 over 4a squared. And then I'm going to add that k squared to both sides of my equation. And that's going to give me this expression right here. So again, this is just this expression from up here, but with my k squared value added to both sides. Now, I know by the way I set this up that this left side of the equation is going to be x plus k, quantity squared, or since k was equal to b over 2a, this is going to be x plus b over 2a, quantity squared. And this is my constant on the other side. Now, before I can solve for x, I want to find a common denominator on my left side of the equation. So I'm going to multiply my minus c over a by 4a over 4a. And that's going to get me this expression, b squared minus 4ac over 4a squared. And now I can solve for x by taking the square root of this expression. Now, the square root of the top is not going to simplify very much, but the denominator is a perfect square. The square root of 4 is 2, and the square root of a squared is a. So that gets me this. And then finally, I can subtract the b over 2a to the other side. And then if I rewrite this with a common denominator of 2a, I get my quadratic form. And so this is the solution that was to be shown. Now, typically at the end of a proof, you will typically mark it with some sort of symbol. Often you'll see a little black square. Sometimes you'll see a double slash. Sometimes you'll see QED. This just means thus it has been shown. It stands for quod erat demonstrandum, which is just the Latin for thus it has been shown. It's again just an indication that I've come to the end of the proof. Now, the second method that we have, as I mentioned, was assume the solution is true, plug it in, and see if it gives you a true statement. So in this, again, this is an algebraic context. We can get away with that. So here I'm going to substitute x squared. X is this. So x squared, I'm going to substitute this in. And now, of course, I have all this computation that I have to FOIL this numerator out. Squaring the denominator isn't a problem, but now I've got to multiply minus b times minus b is b squared, but then minus b times the square root is going to be minus b times the square root. And then foiling again, minus b times the square root again is going to give me two of those. And then this thing squared is going to give me b squared minus 4ac. And this minus plus notation means that where I had a plus before, my equation now has a minus, and where I had a minus before, my equation now has a plus. And then I get this crazy expression. My b squareds can cancel, or they combine rather, to give me 2b squared. And I can reduce this a little bit. You can see there is a 2 and a 2 and a 4. I can factor out a 2 and reduce this if I wanted to. And now I can substitute into my equation a times my x squared and b times my original x plus c. And so what I want to do at this point then is try to simplify, separate these into separate fractions, and then start doing my operations. So here I took out a 2 and canceled with my 4 to make that a 2. And then this a canceled one of these a's. And when I split these into separate terms, I ended up with b squared over 2a. And this one reduced to b times the square root over 2a. And then the a cancels, the extra a here cancels, and things reduce here to just c. If I distribute my b through, I get my b times b is minus b squared over 2a, and b times the square root, I get this, and then plus c. And then what I want to show here, then again, ideally I'd like to explain. So b squared over 2a minus b squared over 2a, they cancel. Here I have minus b minus plus b times b squared minus 4ac over 2a. And then here I have plus minus. So the minus goes with the plus, they cancel. The plus goes with the minus, they cancel. And the minus c and the c also give me 0. And since 0 equals 0 is a true statement, we can see that all like terms do cancel, and thus the proposed solution does satisfy the quadratic equation. Now, another kind of example that we might encounter in Calc 1 is proving the limit definition from the definition of the limit, proving that a limit is in fact the limit using the definition. So here we're given a specific function, 3x plus 1, and the value of the limit is proposed to be 13. So here the definition of a limit is that the limit as x goes to c of f of x equals L is that if x minus c, the absolute value of x minus c is less than a very small number delta, then the absolute value of f of x minus L is less than epsilon, another very small number. So basically this says as x gets really close to c, then that, again, small, a very small, very close to C, then the difference between the function value and the limit will also be very small. Now, in this case, this is going to be one of those examples that we encounter where sometimes we have to do the work in one order and then establish the proof in a different order. So this happens actually far more frequently than you might imagine. So we're going to find a relationship between epsilon and delta, but that won't be the end of it because by doing it the proof this way, we're actually starting with the conclusion, the then statement, and then we're going to find that relationship between epsilon and delta on the if statement. But then we have to, again, make our argument from the if getting to the then, not the then getting to the if. So we will have to reverse the order of our calculations in order to show that going in the correct direction still applies. So there's some preliminary algebra that we have to do, and then we can get to the proof. So the preliminary algebra we have to do is we're going to start, as I said, with this function minus L less than epsilon. So we're going to replace our function and our limit into this expression. We're going to factor out our 3 in this case. And when we solve for absolute value of x minus 4, we get the absolute value of x minus 4 is less than epsilon over 3. Now, because our limit is going to 4, this is our x minus c. And so this epsilon over 3 has to equal delta for this relationship for our proof to follow through. So now we have the pieces that we need in order to do the proof. So now we're starting the proof. So again, we're going to start from that if statement. Let us suppose that the absolute value of x minus 4 is less than delta, and we wish to prove that the absolute value of 3x plus 1 minus 13 is less than epsilon. Remember, this is our function, this is our limit. So to show this, we suppose that delta is equal to epsilon over 3. Then our absolute value of x minus 4 less than delta implies that the absolute value of x minus 4 is less than epsilon over 3. If we multiply both sides by 3, we get this expression. And then we can put the 3 into the absolute value to get this expression. And then we can rewrite this to match the thing we're trying to show, which is that 3x plus 1 minus 13 is less than epsilon, which is what we were trying to show. And so thus, by the definition of the limit, we know that the limit as x goes to 4 of 3x plus 1 is equal to 13. Again, this doesn't need to be long, but you do have to insert words inside your calculation. We've also encountered sometimes doing proofs inside pre-calc when we're doing trigonometry. Now, again, some professors will have you do this in a sort of a more formal way. Some will just have you do this in a slightly less formal way, just showing the steps, the algebraic steps. Hyperbolic tangent you may only encounter for the first time in calculus or maybe differential equations. But when you encounter them, again, the algebra is not all that difficult. It's just that we need to make sure that we're adding those explanations and not just doing computation. Now, again, there's another strategy that we can use. There's 2 different strategies we can use for this one. So the shorter version is going to depend on knowing things that have been previously proved. So for instance, knowing that what the derivatives of hyperbolic sine and hyperbolic cosine are, then you can rely on those definitions in order to do the proof. And that will require less algebra. On the other hand, if you know nothing about these, then you might have to revert to the formal definitions in terms of exponential functions. And then that will require a little bit more algebra because the definitions of the exponential functions are a little bit more complicated. But let us go through, we'll do both examples. They will get you to the same result in the end. Now, this is the longer, nastier version. So I'm going to use the definition of hyperbolic tangent, which is defined as hyperbolic sine over hyperbolic cosine. And when you work out these in terms of the exponential definitions, you end up with this expression. And hyperbolic secant is 1 over hyperbolic cosine, which is, again, the reciprocal of that. So 2 over e to the x plus e to the minus x. And we want to establish that if I take the derivative of this expression, I get this expression squared. So I'm going to replace hyperbolic tangent with this, and then I will need to employ the quotient rule. So notice I wrote this down. I didn't just jump to the next step. So here, again, I'm being very careful. The derivative of the top, the bottom times the derivative of the top minus the derivative of the bottom times the top. And then I actually do the arithmetic with the bottom squared here. Now, in this case, don't FOIL this out. That'll just make your life miserable. So if I FOIL out these components, then I'm going to end up with things, my 2 and my minus 2. Some of these things will survive because this is minus minus, but e to the 2x minus e to the 2x, that cancels. E to the minus 2x and minus e to the minus 2x also cancels. I'm left with just that 4 from the 2 and 2. And then again, my denominator, I don't have to FOIL it out or do anything because it's already in the form I actually want it to be in. It already has this form squared, so I'm good. And so when I cancel out after FOILing, I then just have to write this as a square. And then I can see from my definition of hyperbolic secant that this is in fact hyperbolic secant squared. Again, this is a lot of algebra because you're doing all of the FOILing and distributing and everything. Now, in the second method, we're going to employ our knowledge of other hyperbolic trig functions, that the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. And again, we're not going to go all the way to the exponential definitions. We're just going to stop with the fact that the hyperbolic tangent is hyperbolic sine over cosine, and the hyperbolic secant is 1 over cosine. The steps are basically the same, but because we're not going out to those exponentials, it's a little faster. Here, we're going to take the derivative, again, using our hyperbolic sine over cosine. We're going to employ the quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom. This derivative becomes hyperbolic cosine. This derivative becomes hyperbolic sine. Our denominator is cosine squared. And then we get hyperbolic cosine squared minus hyperbolic sine squared. From this point, we need to employ a identity. For the hyperbolic trig functions, hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. This can be easily proved, but you should show it separately. Here, we're just going to invoke it, and thus this expression will become 1, and then this is obviously hyperbolic secant squared. Again, keep in mind, if you've used no words, your proof is not a proof. You need to explain your steps. It's also very useful to plan out your proofs. Again, sometimes you need to work out certain details in advance. For instance, the relationship between epsilon and delta, or in the last example, the identities that we're using. Again, know your audience. In general, you may assume your audience is the same level as the rest of your classmates, or maybe just slightly behind you, like maybe a week or two behind you. They're seeing this proof for the first time. So if you were encountering the proof for the first time, what explanations or steps are needed to make the proof clear and easy to read? Again, so if you were to read it out loud, the more steps you skip, the more likely you are to need a verbal explanation to support a concise proof. So especially if you're skipping steps, explain, what did I do? Anytime you begin a proof, you should begin by stating your assumptions. If the statement that you're trying to prove, if there are any if statements, you need to start with them. So suppose that, blah, blah, blah. Or proofs frequently begin with from the definition, blah, blah, blah. Proofs, like well-formed paragraphs, have three parts. They have an introduction, a body, and a conclusion. The introduction includes the statement of the proofs that are the proof that's being made and any initial assumptions and definitions. The body carries out the required computations with explanation being the key part. And then the conclusion restates the conclusion of the proof, maybe restates what was proved. If the proof is especially long, in particular, and then it marks the end of your proof with a symbol like QED or the double slash or what have you, again, to separate it from anything that would come afterwards. And of course, when possible, employ theorems to make your work shorter. So if you can invoke other theorems, like in our example with the hyperbolic trig functions, if you can invoke the fact that the derivative of sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine, that made the work much easier. You don't have to go back as far to the exponential definitions. You can, but you don't need to, and that will make your proof easier to follow and more concise. Try not to refer to theorems by the numbers as they appear in your textbook, since these will differ from book to book or term to term, and they might make it harder for people to follow. Instead, briefly state the conclusion of the theorem, since we know by theorem that, blah, 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 or by the quotient rule, which is itself a theorem, you can invoke the name of theorems. Usually that's enough to provide enough information for people to understand what you're trying to get at. But use those as a way to establish facts, and again, not so that you don't have to reprove the results. You can use and invoke those theorems in order to make your work more concise. But again, the key thing here is you need to provide explanations along with your work. If there are no words, it is not a proof. It's a calculation.